Hi, in the previous video, we started discussing customer choice theory. However, we restrained our attention just to the analysis of one single good. Now, we're going to broaden our analysis by the inclusion of more goods. And in order to do so, we need to introduce a bundle. Bundle is a set of goods our customers choose to consume. Sometimes we call them bundles, sometimes they're basket, but basically now we will be talking about these sets, collections of goods customer chooses to consume. However, again, not to make things too complicated, we're just going to start with a very small bundle, XY. When we see something like that, we know that this is a bundle with goods X and Y. However, please notice one important thing. X and Y are in capital letters because where X and Y denote their respective quantities. Okay, so look, this is a bundle with goods X and Y, where lowercase x and lowercase y is telling us how much of each of these two goods we have in our bundle. Okay, so now we have a set of goods that we are going to analyze. However, before the customer can buy these goods, customers, of course, need to know how much money the customer has and how much those goods cost. In other words, our customer cannot buy as much as he or she wants. The customer is constrained in this case. And this is why the next thing we need to introduce is called budget constraint. Okay, and budget constraint is the set of all combinations of good, of all combinations of quantities of goods X and Y. So X and Y, please remember, those are the names of the goods and those are their respective quantities. The customer can afford. And now, look, we're going to assume the customer spends his or her entire income. In introducing here savings or this savings, so like taking a loan, would mean we would have to go into intertemporal choice that we actually going to deal with in the next semester. So let's keep it. So in this case, we're going to add assuming he, she spends his, hers, entire income. Yeah. Okay, so look, now we've got a case like this. Customer has got a given budget, knows the prices of two goods, and is willing to spend his or her entire budget on these two goods. Let's introduce some denotation. So B is going to be customer budget. Customer's budget. Then PX is going to be price of good X. And of course then we will have PY, which is a price of good Y. Okay, so now that we have those, we can put all of this together. Okay, and look, customer has budget B. And this budget can be spent on two things. First, we can spend it on good X, and we can buy X units of good X, but for each of them, we need to pay the price of good, and we need to price PX, price of good X. Then the customer can spend the income, the budget on good Y. And look, what we see over here is actually that if the customer spends the entire income on just two goods, then this relationship should hold true, assuming, of course, that the customer is spending the entire income. Okay, let me explain this with a graph. Okay, look, let's just say that here we have how many units of good X customer has and how many units of good Y. Okay, and let's consider different cases, right? Let's start with corner solutions, right? What if customer spends entire money on good X? This means that the spending on good Y is 0, right? Then we've got the budget constraint. Here we replace with 0. We got PX times X. And we see that if the customer would spend his or her entire income on good X, customer would be able to buy a maximum, right? B divided by PX, right? So if the customer is not buying any units of good X, it means the customer, any units of good Y, the customer will be able to afford B divided by PX units. And look, it makes perfect sense. Look, if we have $100, one unit of good X costs $5, it means that with this kind of money, at most, we can buy 100 divided by 5, 20 units of good X. Right? And look, by the same token, we can go to the situation where we do not buy any units of good X, when budget constraint then turns into PY times Y, and we can calculate that Y max is simply B over PY. So, here we will have how much does the customer wants to buy, can buy, assuming spends entire money on the on good y. Okay, and look, if we notice something, this is a linear function. Look, let me rewrite this function a little bit differently. Let me move this to the other hand side of the equation, right? We get that this is py times y equals to negative px times x plus b, right? Out of this equation. Now, I divide both sides of this equation by py, and then I'm getting something like this. Look, this is nothing more than a linear function that we all know and love really well. This is simply y equals a times x plus b, right? Nothing more, simple linear function. We know that a is negative because prices cannot be negative, right? So we've got a ratio of two prices with a minus. And here we actually got the intercept, right? That we see over here. So what we can see is that actually, if we want to draw a budget constraint, all we have to do is to draw this straight line connecting these 2 points. And look, now let's consider a different point over here. Look, if we have a point like A, look, what can we say about this point? Given the customer's income, the customer cannot afford to buy at the same time this many units of good y and this many units of good x, right? Simply, customer does not have enough money to purchase this many units of good y, right? And definitely will not have to purchase this much of good y and a little bit more of good x. Okay, and look, we can basically say the same thing about every point that lies over here. Here, we have a set of all points, so all bundles, combinations of good x and y that the customer cannot afford. Okay, now, if we look at point B, we see the reverse, right? Look, in this moment, we see the customer has only this much of good y, only this much of good x. Customer has still money left. Of course, this is a possibility, but you remember assuming spending entire income. So we are also not interested in this possibility. So over here, below the blue line, below the budget constraint, we will have all points that customer in which all combinations of good x and y the customer can afford and still will have some money left. So we are taking them up. And look, this leaves us only along the budget constraint. Here we have all the combinations of good x and good y that the customer can actually afford. Okay, so we know that we will be interested in this indifference curve, in this budget constraint. Indifference curve is a second tool that we're going to introduce in a matter of minutes. Now, let me just give you a little bit more information about the budget constraint. Look, because budget constraint can move, right? We see that it actually depends on 4 parameters, right? Like 2 coefficients and 1 constant, right? Prices of goods and a budget customer has to spend, right? So let's see what will happen if we have a given budget constraint, right? And we know that budget constraint is given by the following formula, right? B equals to px times x plus py times 1, right? However, we also noticed that this can be easily translated into this equation, right? Y equals negative px py times x plus b over b over p. And look, what we are going to do now is that we're going to examine what happens if something changes here. And let's say first budget goes up. What does it mean? Look, it means that now we've got more money to spend. This means that we can both more good x and good y. So look, what is moving up? This is going up, this is going up. Assuming that the prices are the same, what will happen? We will have new budget constraint that is parallel. Of course, this is a straight line. I'm sorry, not an artist. I don't have a ruler in my eye. But this is a parallel shift, right? Because now we will have here a point where we can afford more of good y and more of good x, right? And this is a parallel shift, right? Look, it makes perfect sense. With higher this, we will see it as b going up. So our linear function is simply moving upwards. Okay, so we see that every time when customers' budget increases, we will see that customer can buy more of both goods. So we will see this one as a parallel shift upwards, right? Parallel shift upwards. And consequently, customer will have better choices. And of course, it works in the opposite direction. Of course, if B is going down, we will see as a parallel move down. Okay, but that is the first possibility, right? The second possibility of things that can change are prices. However, look, here, what matters the most is relative price. Relative price means the ratio of these two prices. Look, the slope of budget constraint is plainly given as the negative of the ratio of two prices. So look, this means that if one of the prices is changing while other is being kept constant, the slope will have to change. For example, what will happen here if price of good X will go up? Look, we clearly see that now from the first equation, a customer can afford less of good X, right? But look, it means also that here we will be dividing by a bigger number. Look, if budget at the beginning is 100 and price of good X is 10, you can buy 10 units of good X. But if price goes to 20, you can buy only 5 units, right? So we had 10 units at the beginning, we would have 5 later. And look, the same to happen over here. Because Px is going up, it means that this number is becoming bigger in absolute terms, but it has minus up front, which means that the line here is simply becoming steeper. So we will see it as pivoting around that point. That point stayed the same because we assume that price of Y did not change, so we can still buy the same amount of good Y. Of course, we can do exactly the same trick for price of good Y. Of course, now remember, as it happens, that if prices of both goods increase in the same proportion at the same time, it can look like a shift of a budget, but let's just say that this is like a very rare possibility that could happen, that is just interesting, but doesn't really bring that much into the analysis. Okay, we know the basics, so we know that supply side, right? We know what is the income of the customer, right? Now let's go to customers' preferences. And of course, look, preferences of customer are again a little bit harder to quantify than we had, which is budget and prices. These things are just true, right? Because this is how the word is constructed. If you have $10, price of a pen is $2, you can buy at most 5 pens. This is how it works, right? However, with preferences, we have a little bit more of a complex issue. We already touched upon this subject in a previous video when we were discussing concept of total and marginal utility. So now that we have a budget constraint, we need to also add to this picture some representation of customers' preferences, needs, what the customer wants. And for this, we use a tool that is called indifference curve. Okay, and again, let's start with a precise definition. So this is a set of all combinations of quantities of good y, good x and y. So we know that those are denoted by x and y. Name of the goods, their respective quantities, right? For which the customers receives receives the same total utility. Okay, what does it mean? Look, now we have now we are interested in finding different bundles, different baskets of goods for which customer is indifferent, which means the customer would say, this good and this good, I take either one. I like them, this basket or this basket, I like them the same. Let's just say that you go to a restaurant, you go to a McDonald's, let's just say, right? And you're indifferent between getting 2 cheeseburgers and a french fries, bags of french fries, or 2 bags of french fries and 1 cheeseburger, for example. So basically what we are trying to see now is we try to track all those combinations that will bring the customer exactly the same satisfaction. Okay, now, how to approach this mathematically? Look, as it turns out, there's a very simple trick to it. Okay, look, we are going back to total utility function that we introduced last time. However, now the utility function is a function of a bundle of 2 goods, X and Y. Now look, if I want to say, I want to find a level of I want to find combinations with the same level of satisfaction, I can assume that this level is equal to some C, a constant, right? It doesn't really matter what the level is. We know it's a certain level. What can I do now? Well, look, now what I can do is to differentiate this equation. Calculate a differential, right? So we will have du, right? Which will be equal to ux dx plus uy dy. Of course, please remember that ux, I just calculated total differential, right? So this, in here we have 2 possible sources of change in x. Changing the quantity, changing utility, changing in the quantity of x consumed, or changing the quantity y consumed, right? So remember, this is simply total differential. Ux is nothing more than the first derivative of the utility function with respect to x. So this is marginal utility of good x. And here, of course, we will have by the same token, uy, which is partial derivative of utility function with respect to good y. So this is marginal utility of good y. Okay, and now look, there's one, so here, we dealt with this, right? We've got an expression that gives us change, 2 possible sources of change in level of utility. However, we want this change to be equal to 0. Why? Because we want to assume a certain level of customer satisfaction, so a certain level of total utility. So look, if I differentiate a constant, I'm getting a 0. And look, turns out that even without knowing the exact form of the utility function, I will be able to find the slope of utility function just from that. Why? Because look, I can, for example, just take this and put on the other hand side of this equation, I get duy dy equals to negative ux dx, right? And now if I divide both sides by dx and uy, I'm getting dy dx equal to negative ux over uy. And what you see over here, this expression, which can also be negative negative of marginal utility of good x divided by marginal utility of good y, is the slope of the indifference curve. Okay, so look, we found slope of indifference curve. Is it positive or negative? Look, marginal utility tells us by how much utility total changes when we consume next unit of x. If we consume more, we are happy, right? So this is positive. By the same token, this is positive. Ratio of two positive numbers with a minus up front must be negative. So we know the slope of indifference curve. We know it is negative. Can we say anything more? Actually, it turns out that this slope of indifference curve, has a very special name and has a very nice economic interpretation. So, negative of marginal utility of good x divided by marginal utility of good y is something that we will call MRS, or marginal rate of substitution. So, what is this marginal rate of substitution telling us? Well, it tells us how many units of good X the customer is willing to give up for one additional unit of good X while maintaining the same total utility. Utility. Okay, so look, generally, this marginal rate of substitution is telling you on margin how much the customer is willing to give up for one good for one additional unit of the other. And as it turns out, we know about some properties of this marginal rate of substitution, and those properties will allow us to draw the graph of an indifference curve. And actually, again, in order to understand what is happening, we're going to resort to the idea, we're gonna resort to the idea of total and marginal utility for individual goods. So, the board actually changed, and now we are ready to derive indifference curve. And look, I'm going to start by showing you how the indifference curve looks. It looks like that, right? It is a convex function, right? We have a decreasing convex shape, and it is downward sloping. Does it make sense? Well, it should. Why? Well, we know that marginal utilities are positive, right? If we consume more of some good, we get additional satisfaction out of it, right? So, of course, minus up front makes perfect. Minus up front makes this into negative expression. Okay, but look, the main thing here is to explain why the shape of it looks like that. And look, we can do formal proof under a given set of assumptions. However, as this subject you will be dealing with in intermediate microeconomics in very much detail, all I want to do now is to actually give you the best intuition, of course, in a little bit more mathematized way. Okay, so look, I denoted 3 different points on this indifference curve. Look, we've got a case like that. Our customer chooses between 2 goods, good X and good Y. Now, lowercase x and lowercase y again represent their quantities. And look, let's assume that we are at point A. Look, at point A, we see that customers has, let's just say, YA of good Y, right? And XA of good X. Look, so we clearly see from that customer has a lot of good Y and just a little of good X. Okay, now, if the customer would consider these goods individually, now we can resort to what we learned already about marginal utility for a single good and extend it to the case of 2 goods. Now follow. Look, if we have a given amount of good Y, then we expect that when we have more and more and more of good X, right, then utility increases, but of course slower and slower and slower. And the same for good Y, right? So look, we see that here actually the correspondence is to point A. And look, at point A, the customer has very, very little of good X. What does it mean? The total utility the customer gets from a consumption of good X is small. However, at the same time, look, marginal utility is high. What does it mean? It means that getting additional units of good X would bring the customer a lot of additional utility. Okay, and now look, if we look at what is happening now for good Y, we see the customer has quite a lot of good Y. And what are the consequences of the customer having so much of good Y? Well, it brings him a lot of utility, but he's not valuing this. He's not valuing this very much. Why? Look, because he already has a lot of good y. So getting a new one would get him only a little additional utility, and actually sacrificing one would also mean that the customer would only sacrifice just a little of additional utility. And this should show us what is actually happening over here when we will move from point A to point B. Okay, and this is where we stop, right? Okay, so what can we say that is happening at point A? Look, at point A, we know that marginal utility of good X is high, while marginal utility of good Y is low, right? So what does this tell? What is this telling us? If this is a big number and we are dividing it by a small number, we should get a number that is relatively big, right? And because if we get a big number with negative sign in front of it, what are we receiving? We are receiving a line that is downward sloping and very, very steep. So we get a gist of the mathematical connection over here, definitely. But look, economic interpretation closely follows. Okay, look, what is happening when I'm trying to move from point A to point B? Look, let's start with the choices of the customer about good X. Look, customer has just a little of good X, right? So in order, so customer values good X a lot. And remember, main thing about indifference curve is that the total utility on indifference curve is given by some constant. Okay, maybe. Which means that over here, each bundle over here will give the customer exactly the same total utility, right? This is where we get this condition, du equals to 0. Okay, so look, we are considering move from A to B. So we are going from bundle that is really abundant in Y, and X is scarce in this one, right? So we know that the customer is valuing good X a lot, while at the same time, good Y not much, right? Customer already has a lot of it, right? So what is happening here? The customer will be willing at the beginning to give out a lot of good Y, right, for relatively little more of good X, right? So look, when we arrive from point A, when we move from point A to point B, we see that now, right, the customer increased the possession of good X by definitely less than the customer decreased the possession of, the possession of good Y. And look, this is the this is the fall in this is the fall in utility, right? Marginal. So basically, this is this entire marginal utility collected, right? And look, but here we see that now customer has way less Y, right? While at the same time, a little more of X. Why is that? Look, it's because customer had a lot of Y, a little of X. So was willing to give up a lot of Y for a little of X and still had exactly the same total utility. And look, now when we move to point like point B, this point B is a situation where the customer has let's just say equal amounts of both goods. Okay, and what is this telling us in this example, right? We are at point B, right? And we are asking now, what would happen if I wanted to move from point B to point C? Okay, so the thing is here, that situation is now has changed a little. Now the customer has more or less the same amount of two goods, right? In a, let's just say, more or less equal proportions. So the good good Y is no longer so abundant, and at the same time, good X is no longer so scarce. So now, if the customer is to keep the same total utility, if we want to take him yet another unit of good Y, right? Here we would have the fall in the possessed number of good Y. What would we have to do? We would have to increase the possession of X quite substantially, right? Why? Because look, now a customer does not have that much of good Y. He values it a lot. So to maintain the same total utility, you need to increase X by more. Why is that so? Look, because now, when we are at a point, like the point C, the situation here is completely reversed, right? Look, which total utility, which marginal utility is high? Well, now that we have very little, very little of good Y, this one is going to be high, and this one is going to be low. And look, if we divide low number by a high number, we get a relatively low number, and we see that over here, this part of indifference curve is actually flat. Okay, and look, basically, we could do the same thing for every point, and we would get this shape. Look, as we have very little of good X, we need to be compensated by a lot of good Y to maintain the same total satisfaction, total utility, and it works vice versa. If we have only a little of Y, to maintain the same total utility, we need to have more of X, way more of X, right? And of course, we would expect that because of that, the function will have this specific shape. Okay, and look, this is more or less formal, a more or less formal explanation why does indifference curve behave in such a specific way. But let's just say a couple more things about indifference curve. Because look, what is important to us, of course, is to figure out, how customer is achieving the highest possible utility, right? So we need to know a little bit more about indifference curves. The first question that usually pops to the mind is whether the two indifference curve could intersect, right? So let's start with this. Let's start with this problem. Okay. So here again we've got y, here we've got x, and let's just say that here is one indifference curve. This is a second indifference curve. And we've got 3 points of interest. Let's just call it A. I'm sorry, y, A, x, A. And then we've got a point like B. And finally, we've got a point like C. Point like C, okay. Okay. And look, let me ask you a question like that. Which of the 3 points is the best for the customer to be on? Well, when you think about it, well, the answer could be relatively easy to establish for points A and B. Why? Well, look, when you look at this part of the picture and you ignore this, we can clearly see that doesn't matter how we look at it, point B is inferior to point A, should be inferior in eyes of the customer. Okay? Look, we write it like this. B is preferred to A, right? So we see here that bundle B is preferred to A, and bundle B in this case is better because. And let's look at it. Look, what can I see over here? Look, I see over here that definitely YB is bigger than YA, right? So in this basket, bundle, the basket is okay, the customer has more of good Y than in basket A. But look, I can say exactly the same thing for good X. In basket B, we've got more of good X than in bundle A. So, we clearly see that B must be better than A, right? So, this is because XA is smaller than XB, and at the same time, YA is smaller than YB, right? No issue here. However, look, if I were to compare point B and point C, this becomes problematic. Because look, on one hand, at point B, we see that in bundle B, we've got definitely more of good Y. However, at the same time, in bundle C, we've got more of good X. So which one is better? And look, we can decide upon it using what we already learned about indifference curves. Because what? Look, each point at indifference curve gives the customer exactly the same satisfaction, exactly the same total utility. So, based on that, I can say that customer is indifferent between bundle A and bundle C, right? So, customer is indifferent between bundle A and C. Why? Because they are on the same indifference curve. Okay, so what can we now conclude? Look, let's combine what we've learned over here. We know that B is preferred to A, and we know that A is indifferent for the customer to C. So, what conclusion can we get out of it? Well, we definitely can get that if those two have the same utility and this one is bigger than this one, we can see that B should be preferred to C. Right? So look, we can actually learn two very important things from this example. First thing is, two indifference curves can never intersect as long as the transitivity property holds. Transitivity property is something you've learned in high school, probably even. You will learn a lot about it in microeconomics. But it's a basic idea that we accept quite easily. It generally goes like this, that if customer prefers or is indifferent to between A and B, and prefers or is indifferent to B to C, then we should expect, and this implies, well, that this tells us that A should be preferred to or equal to C. Okay, and look, this makes perfect sense, right? Let's use strict inequalities here, right? It still should hold. And look, does it make sense? Look, when you think about it rationally, this is how it should be, right? If you prefer ice cream to cake and cake to apple, you should definitely prefer ice cream to apple. However, we should expect that people follow it. Let me just, as long as this condition is fulfilled, right? we know that indifference curves are not going to be intercepted. But look, it has a deeper consequences. Like if we would not follow this, we would be in a big trouble. Why? Because we would be constantly losing money. And let me illustrate this by this very simple example. Look, over here we see that customer prefers A to B, B to C, and A to C. In this case, we see that this is not consistent, right? It should not be like this. And let's just say that this is person 1 who prefers bundles like this, and there is a person 2. Person 2 is aware that the person 1 has this very unusual preferences that do not follow transitivity properly. Okay, so let's say that at the beginning, number 1 has 2 bundles, A and B, and it has $3. And let's just say that the second customer has just C. Okay, and look, this one comes to the other, second one comes to the first one and says, you know what? I know that you prefer C to A. If you give me $1, then I will give you, I will exchange C with A with you. And he says, okay, so look, what happens? $1 goes from customer 1 to customer 2, and C is exchanged for A. And then he says, I know that you prefer A to B. I will exchange it with you for $1. He says yes. So this person gets another $1 and is exchanging for that B for A. Okay, and then finally he can say, I know that you prefer B to C, I'll exchange it for $1. This person now has $0. This person has $3. This person has C. And this person has B. And look, after these 3 rounds of exchanges, what do we see? Person 1 has exactly the same 2 goods. And the same goes for person 2 who has the same, now has C, but the money was exchanged. Look, if your preferences are not consistent in this way, if they do not follow this transitivity property, you will always lose money. Okay, so if we know that our customers are rational enough to figure this out, we can be sure that indifference curves are never going to intersect. However, this is not all that we learn over here. Look, second thing that we learn is about where the customer wants to be. Look, we clearly see that point B is better than point A, but it means that every point at indifference curve U2 is better than any point at U1. And look, by the same token, you can imagine that if I would draw here U3, then if there would be a point D over here, we would see clearly that point D is superior to B. So we can expect that this indifference curve is going to be better than this one. So look, The final thing we should get from this is that customer maximizing his total utility tries to get on the highest indifference curve possible, right? So, look, indifference curve represents utility, right? Represents preferences. Then, of course, the customer wants to get on the highest possible, right? Because this one is going to represent the highest attainable utility. However, a customer cannot just choose where he wants to or she wants to be. Why? Because the customer is constrained by budget and prices of the goods. So the two things we discussed at the beginning of this video. Now, how do we deal with this problem? So, how will the customer decide what to buy given budget and prices? To solve this issue, we're gonna use Lagrange multiplier that we reviewed a couple of videos ago. And then we're gonna see what is the main cornerstone of the customer choice theory. Okay, see you in the next video.